Okay, the goal is to finish off Unit 2 in this lecture. So where we were last time, we had finished off with addition reactions of alkenes, this time using unsymmetrical reagents. An example would be the hydration of an alkene, where that reagent is considered unsymmetrical because we were showing it as H, covalent bond, OH. So that's an unsymmetric environment on either side of the covalent bond. So hydration of an alkene was an example of that, as was hydrohalogenation of an alkene. Now, we ran into an issue when we reacted one of these unsymmetrical reagents with an unsymmetrical alkene, and ended up with the potential for two products. And if we have a difference in substitution patterns on those two products, we can use Markovnikov's rule to predict the major product and the minor product of reaction. In this case, this is a hydrohalogenation. It also works with a hydration of alkenes. And lastly, we took a look at a more practical aspect of organic chemistry, or specifically with alkenes, that of addition polymers. Addition polymers, all you need is an alkene monomer of any type, and you can polymerize it using these addition polymerizations to come up with materials. And these different materials had different attributes associated with them based upon their substitution pattern on that alkene. So now we're going to get into the last piece of these unsaturated hydrocarbons, and that is titled as aromatic hydrocarbons. Aromatic. We've had some insight into an aromatic hydrocarbon up to this point, and we'll cover that in just a moment. But an aromatic system, or an aromatic hydrocarbon, is always a six-membered ring, a ring with six carbons, with alternating double and single carbon-carbon bonds. Over on the right-hand side now, we have a couple of examples of really a naked aromatic ring, just the ring itself, and that can be drawn in complete bonding structure, where we have all the carbons and hydrogens and bonds and that sort of thing put in there, or we could draw in a line structure. But this ring system is the core, the basis of what an aromatic hydrocarbon is. And we find that these double bonds in our aromatic rings are not like normal alkenes. They're not like normal, they don't react like normal alkenes, they don't behave like normal carbon-carbon double bonds, which are alkenes. We find that these double bonds, if we look over on the right, these double bonds, alternating double bonds in an aromatic ring, they exist as what are called resonance hybrids. Now, meaning that these double bonds are not stationary within the ring. So if we look, we have this sort of back and forth arrow here, and two representations of the same compound. If we look at the compound over on the left, we see this is an aromatic ring which is substituted. It happens to have an ethyl group poking off of it and a methyl group. That we'll look at those examples when we start talking about nomenclature. But really what I'd like you to look at here is the aromatic ring itself. What ultimately happens is these double bonds can sort of domino sort of flip over to where the single bonds were. And we see this happening here. And then look over at the structure on the right. Well, the rings, or rather the double bonds, seem to have swapped. And indeed they do. They swap places. But both of these are reasonable representations of what this structure looks like. It doesn't matter where we place the double bonds within that aromatic ring, as long as they are alternating, double, single, double, single. And you'll notice in this case that we have this back and forth arrow right here. As soon as we flip our double bonds and get over to the product, or this rendition on the right, they flip again, as shown here, and we end up with the rendition on the left. And it's a back and forth sort of thing, a constant back and forth sort of thing. So we really don't know exactly where those double bonds are on that ring. Sometimes they're single, sometimes they're double, to the point where we can actually draw an aromatic ring with in a sort of an abbreviatory way. We still have that hexagon to show that there are 6 carbons within there at each bend, but instead of putting alternating double bonds in there, we simply draw a circle. And we draw a circle to show that it represents these double bond electrons always on the move around the ring. They never stop moving around. You don't have to draw it like this. It is just a way of expressing that. So I could draw this compound like I see here, or I could draw that same compound like I see here, minus the curved arrows, of course, but they're both perfectly reasonable renditions of drawing that particular compound. And I tell you this not because you must draw it one way or another, but because you will encounter aromatic rings sometimes that have just that circle within there, and sometimes you'll encounter them drawn with the alternating double and single bonds. One thing you wouldn't do, however, is to draw it with the circle in it as well as putting in those alternating double and single bonds. You can't have both. It's either one or the other. So if we look at some of the connotations of the fact that we get these double bonds within an aromatic ring constantly being on the move, can never pin down these as actual alkene double bonds, we find that this speaks in terms of reactivity. The carbon-carbon double bonds in an aromatic ring are not reactive like normal double bonds, carbon-carbon double bonds in alkenes. And I can show a sort of a side-by-side example. If I had an isolated double bond, like I have on this example over on my starting material here over on the left, and if I treated that with molecular bromine, I'd get a spontaneous reaction to get this dibromo species over here on the right. And we spent a good amount of time looking at examples, halogenation of an alkene. However, if I treat an aromatic ring with molecular bromine by itself, I get no reaction. So this double bond here is not around long enough to react. As soon as bromine goes in for the kill right here, well, that double bond has become a single bond, because remember, those double bonds are moving in resonance around that ring, so you can never quite pin it down, and poor bromine can never get in there to react as they could, say, with an isolated double bond. That doesn't move. That it stays right where it is, so bromine can easily react with it to form that dibromo species. Not so when we treat molecular bromine with a compound such as this. Now, we will be getting into, in fact, the halogenation of aromatic rings with molecular bromine or molecular chlorine. It's just that we have to sort of kick it in the pants with a very strong catalyst, which we would put over the arrow. And what would happen is not an addition reaction. Remember, addition reactions are specific for alkenes. We'd get another type of reaction of a halogen with an aromatic compound. In fact, it's a substitution reactions, which were similar for alkanes. But we'll get into that towards the end of this lecture. Now, so we can say what we can say as a conclusion is that these carbon-carbon double bonds in an aromatic ring have a higher degree of stability, or rather non-reactivity, than alkene carbon-carbon double bonds, notably because they are always moving. So we can never pin them down to react as a normal alkene can. So now that we've defined sort of how an aromatic ring ticks, we'll move into a nomenclature series, a nomenclature of aromatic hydrocarbons. And the simplest aromatic hydrocarbon is simply the ring. And that is actually a compound known as benzene. Benzene is a common, or not so common now, but it used to be laboratory solvent. It's a clear liquid at room temperature, works fine as a laboratory solvent. But we'll be talking about the benzene in terms of nomenclature. Now, we can have this naked benzene ring, or as we saw before, we can decorate it with substituents. So this would be an example of a substituted benzene ring. We popped a chloro on one of those carbons and an ethyl on another. We'd be able to, by the end of this unit, we'll be able to name that compound. And it has similar nomenclature to what we've looked at before, with certain quirks that are specific for aromatic hydrocarbons. Now, we said that we have our benzene here. When we just have an aromatic ring, it is called benzene. But if you'll remember, we've been associated with, or we've seen an aromatic ring before when we were talking about functional groups. And one of our hydrocarbon functional groups was the phenyl group. When we have an aromatic ring as a substituent on a larger parent structure, it was known as the phenyl group. And a common misnomer or mistake is to call that now a benzene group as a substituent. It is not. It is called a phenyl group, something we've looked at before. And so it's important to make that distinction. It's tempting to call that, well, that's a benzene group, and here's a chloro group, and that sort of thing. No, it's a phenyl group. So with benzene and substituted benzenes, the aromatic ring is always the parent structure. And when this happens, frequently, if not most of the time, the term benzene, or a contraction of benzene, is part of the name, the actual name of that parent compound. Remember, we're looking at aromatic parent compounds right now, and I'm going to show a listing of them. And all of these parent compounds are going to be a singly substituted benzene ring. And as we'll see, many of them, if not most of them, will have the term benzene, or a contraction thereof, as part of the name. So let's look at the first one. What if we took a benzene ring and popped a methyl group on it? Well, this is known as methylbenzene. Pretty straightforward. Methyl, because that's the substituent. Benzene, because that's the parent. Methylbenzene. Now, as we'll see sometimes in these aromatic compounds, frequently there are competing sort of colloquial names. Remember, names that these have had before the onset of UPAC terminology. Another more colloquial way of naming methylbenzene is toluene. Toluene is a colloquial name. It means the same thing. Toluene is actually, or methylbenzene if you like, is actually another common laboratory solvent. It's a clear liquid at room temperature, and thus can be used as a laboratory solvent. So methylbenzene sort of makes sense. So what if we put another substituent on there as a parent, on that benzene ring as a parent structure? Well, what if we put an ethyl group on there? Well, ethylbenzene. What if we put a bromo group on it? Bromobenzene. We're starting to get a flow here. A chloro group. Well, chlorobenzene. And indeed, as we're sort of moving through this, we see that in each of these so far, we have the term benzene in the name. And the substituent is written first. This is quite straightforward. Now, I'd like to introduce a functional group that we didn't look at before when we were laying out all of our functional groups. First of all, because we're not going to see it that much. But it tends to pop up only, or most of the time, only on aromatic rings. And that is known as the nitro group. It's NO2. That one single covalent bond going to that red squiggle, that would be connected to, say, an aromatic ring or something. But NO2 is considered a nitro functional group. And if we put a nitro group onto a benzene ring, well, it becomes the parent structure, nitrobenzene. Again, I haven't introduced this functional group until now because most of our functional groups were sort of decorated onto an alkane system, non-aromatic. But again, as we find, nitro groups tend to proliferate on aromatic systems. They're more stable that way. So in all of these cases now, we've seen benzene in the name and the substituent as the front runner for it. We're going to get into some parent structures now which don't necessarily have benzene in the name, but we have a contraction of benzene within there. Notably, if we look down on the next row, we have an aldehyde group. If I had an aldehyde group covalently bonded to an aromatic ring, it's called benzaldehyde. No benzene in there, but benz is sort of a contraction of benzene aldehyde. Benzaldehyde. That is indeed an aldehyde connected to it, so it's considered benzaldehyde. I could take an aromatic ring and pop on a different functional group, such as a carboxylic acid, and then I would have the parent structure known as benzoic acid. Again, benz as the contraction of benzene, and oic acid, the word acid is the key here because this is a carboxylic acid functional group, benzoic acid. So a couple of these now, while they don't have benzene in it, they have a contraction of benzene in it. So we see that echo within it. There are some parent structures, however, that have colloquial names that are lost in antiquity, and they just have endured through, so we have to sort of memorize them. If I had a benzene ring with an alcohol functional group on it, that is known as phenol. Phenol. OL suffix because it's an alcohol functional group we could look at. But now we're bringing in, it sort of looks like the word phenyl group, phenyl, which is an aromatic ring, which is a substituent on a larger parent structure. So sometimes we just change a vowel. We've seen that before with alkane, alkene, alkyne. Now we see it with phenyl versus phenol. Very different sorts of things, but differing only by one letter. So phenol is the parent structure we see here. Another one off the beaten track is if I took an amine group and an amine functional group and attached it covalently to a benzene ring, I have what is known as aniline. That is an aniline structure, which is an aromatic ring, another aromatic functional group or parent group that we're looking at. Lastly, and this is sort of a weird one, if I have an aromatic ring which is attached to an oxygen, which is then attached to a methyl group, as we see here, that is known as anisole. Anisole as a parent group. These last three, again, being examples of colloquial names, sort of, that still endure today. So let's look at some examples of where we could use some of these parent groups, naming structures which have other functionality attached to the aromatic ring. Okay, so here is a structure. We have it's clearly an aromatic ring. We have a couple of substituents on it. We've seen an example of that before, but our task right now is to determine what is the parent structure. And if we look at this, we could say that, all right, well, what if I traced out this area right on here as the parent structure? And we would recognize that as bromobenzene. It's a bromobenzene. Now, when we have a substituent on our bromobenzene, we have to be able to address that substituent. What carbon does that substituent reside on relative to the structure with that's the functional group which is already on the parent structure? That bromo group on the parent structure is connected to the carbon which will always be 1. That is the 1 carbon. And as we've done before with cyclic systems, we have to count around the ring in the direction which will give the substituent the lowest numerical designation. And I would hope that you would be able to see that if we count clockwise, that brings in that now ethyl group, which is attached at the 2 carbon. That is an ethyl group. It is 2 carbons, and it's at the 2 carbons. So this would be put on the front of that name, 2-ethyl bromobenzene. 2-ethyl bromobenzene. But now we're going to get into sort of an attribute of naming aromatic systems where we have a little bit of leeway. How about, this is another of the same structure here, but how about I looked at that a little differently and cocked my head over and I said, well, you know what? The parent structure there looks to me like ethyl benzene. Remember, ethyl benzene was one of our parent structures. So I'm going to say ethyl benzene is my parent structure. Now numbering that, now the bromo would be a substituent, but the ethyl group on ethyl benzene always takes that one carbon designation, and now we would have to count around the ring in the direction which gives the other substituent the lowest numerical designation. In this case, we'd have to go counterclockwise, which would bring the bromo group in as the 2 position as well. So this would be now 2-bromo ethyl benzene. Which is it? Well, as a matter of fact, it's both. We have leeway here. In fact, that this structure can be named 2-ethyl-bromobenzene, or, if you like, 2-bromo-ethylbenzene, both of which are absolutely a reasonable name for it. So we have options today when we're naming aromatic hydrocarbons. Let's look at a couple other examples. Okay, well, I have 2 examples here. One is a structure. In that structure, I'm going to be asked for a name, and the other one is a name, and I'm going to you're going to be asked to draw the structure. So let's look at the one on the top first. We would have to figure out where my parent structure is. That's clearly an aromatic system, so we have a number of parent structures which we can think about, which we'd be able to capture in here. And if you look carefully, well, I would say that aromatic ring connected to the oxygen, which is in itself connected to the methyl group, I know what that is because we looked at it on one of the previous slides. That's one of our parent structures. That's known as anisole. Now, one of those weird colloquial names, anisole. And that O-methyl substituent on anisole gets that 1 designation because we have now not 1 but 2 other substituents, a couple of fluoro groups on there. And now we have to count around the ring in the direction which will give the substituents, both substituents now, the lowest numerical designation. So we would count around clockwise in this case, bringing the fluoro groups at the 2 and the 5 carbon on that aromatic ring. Note that if I counted around the other direction, that would bring the fluoro groups in at the 3 and the 6. That's a higher numerical sum. So we're stuck with going around clockwise. We know which way we have to go around. So we see we have 2 fluoros at 1 at the 2 and 1 at the 5 position. So this would be 2,5-difluoroanisole. 2,5-difluoroanisole. So using these UPAC-esque routes or rules that we can very easily, or through, I don't like to say easily, but sequentially come up with that name. Let's look now at the one on the bottom. 2,4,6-trinitrotoluene. Oh, okay. Well, toluene, that we always start at the back. Toluene, that was the colloquial term for methylbenzene. If you remember, that was one of our parent structures. So I'm going to draw in methylbenzene. And that we have that 1 position where the methyl is on methylbenzene, and I can count around that ring since I'm going name to structure in any direction I want. I tend to favor clockwise, so I'm going to draw them all in 1, 2, 3, 4, 5, 6, and now I have addresses for my 3 tri-nitro groups at the 2, the 4, and the 6 position. So I'm just going to affix nitro groups at the 2, 4, and 6 position, and there I am done. It is very much like following a recipe when we go from name to structure, and I have indeed followed that recipe. This is an interesting compound. Actually, it is considered a high explosive. If we look at the acronym here, trinitrotoluene, T, we get N, and we get T. That's TNT. High explosive. So this particular compound here is used in bombs and explosives and so on. So, you know, it's always good to throw in a little sort of interest level, if you will, with organic chemistry, much as we did with the addition polymers. All right, so finally we find ourselves here again at the reason that we are in this course. We're actually going to carry out some chemical reactions of specifically aromatic hydrocarbons. And we're going to find that benzene itself, or aromatic rings in general, do not undergo addition reactions like normal alkenes. Remember, alkenes like those carbon-carbon double bonds, and we'd add over them. But that doesn't work in the case of an aromatic ring, because those double bonds, remember, are zipping around the ring in this resonance going around the ring, so they can never be pinned down to react with the reagent in an addition fashion. In fact, benzene and aromatic rings undergo substitution reactions like alkanes did. Remember a substitution reaction? We had our starting material and our reagent, and the reagent and starting material traded things. That's the reagent traded gave the starting material something, and the starting material gave the reagent something, so that we always end up with a product and a side product of that reaction. I've put that here almost exactly as we're going to be seeing it. We end up with a fragment of the reagent on the aromatic ring, and the hydrogen that was on that carbon of the aromatic ring over as a fragment of the reagent. So there are three reactions of aromatic hydrocarbons that we're going to be taking a look at. One that I alluded to before, the halogenation of benzene. Next, we'll look at the sulfonation of benzene, and also the nitration of benzene. A couple of these are, we can predict right away what the reagent is. Halogenation, well, maybe the reagent is a halogen. Nitration, well, maybe it's a nitro group, or the donator of a nitro group. But we'll first look at the halogenation of benzene in a general sense. So in this very general sense, we have our aromatic ring. We're going to be using just naked benzene for the starting materials in most of these examples. That's why they call it reactions of benzene, not reactions of aromatic rings, because it can get a little bit complicated. But here we have our naked aromatic ring, our benzene, and X2. Now, X in our organic parlance has typically usually been a halogen, and that is either chlorine or bromine. Those two halogens we use diatomic, Cl2 or Br2, given by this X2 right there, can be either one. But we have to add a particular reagent here. And that reagent is an iron catalyst given here over the arrow, and it's given as FeX3. Now, the reason this X in there is because whatever we have as our reagent, whether chlorine or bromine, so must exist on that halogen. I mean that catalyst. So if I have Cl2 as my reagent, the catalyst would have to be FeCl3, right? And if I had Br2 as my reagent, the catalyst would have to be FeBr3. That's why we're using this X here, because X on one must be X on the other. And this reaction proceeds just fine in a substitution sense. So let's see what happens. So we had over on the left-hand side X2. Well, one of those X's ends up single one ends up on the aromatic ring, and the hydrogen which existed on that aromatic ring, we didn't draw that in, remember, because it was line structure. Well, that ends up in my side product as HX, covalently bonded to X. So what we have are these acids, HCl or HBr, as the final product. Given in this substitution sense, a substitution reaction. As always, however, we like to play what's in the box when we're working with these sorts of things. So let's look at a potential what's in the box sort of reaction. Okay, so here we go. We have to look at these always like a detective or a sleuth. Here I have benzene, an aromatic ring, and I have Cl2, chlorine, with FeCl3 catalyst over the arrow. So that's all good information. And then we are asked to put what's in that box, but we're also cognizant that we have this HCl side product here. All of these point to a particular reaction. And with some practice, it would point you to the halogenation of benzene. So let's look at this, and we'll enunciate the business end. One of the carbons on this benzene ring I'm going to enunciate, meaning I'm going to show that carbon and I'm going to show the hydrogen attached to it. And also Cl2 is going to become Cl, covalent bond, Cl. Just to be able to see this substitution. And what ultimately happens in this substitution is, well, a piece of the reagent goes over to and sits on or connected to the benzene, and a piece of the benzene goes and gets connected to that reagent. That's a true substitution. So what we end up with is, and I've color-coded it here to make it seem a little bit more obvious, this is what we ultimately get out of the reaction. HCl is shown over on the right. That's clearly, we've already shown that, but what's in the box, again, I can just write that as a line structure. That carbon that we see right there now becomes just a bend, but that's okay. We have gone through this meticulously with color coding in order to show that, well, this is the product of the reaction. Notice what we have here in the box. That is a monohalogenated product. I had that term on the previous slide. Monohalogenated. Mono meaning one, only one halogen on there. Monohalogenated. And the reason I say this, and it might be obvious, but because some people tend to put that 2 right there. That substituent is a Cl2. That is wrong. It's a single substitution. That other Cl on there is right. That other chlorine is on the HCl right there. So that we have to be careful to account for, well, one chlorine atom goes over to the benzene and one chlorine atom stays, so that we can have a side product. So again, sometimes the game what's in the box can be a little fickle. It's not always the product of the reaction we're looking for. In this example right here, we have a reagent we're being asked for, and the conditions that we're being asked for over here, over the arrow. So in this case, we would have to, again, try to play the detective and say, all right, what's going on here? I have a benzene ring, and it is being substituted with a bromine atom. Bromine. Oh, okay. So that's the halogenation of benzene. That would bring us into around to say, all right, so that means my reagent must be molecular bromine, Br2, and with that, we had that iron catalyst, FeBr3. Notice the halogens must match. Bromine on one must be bromine on the other. Not the number of them. Notice here I have Br2 and FeBr3. It is important that we don't have to always stick with the same number of them, but it has to be the same halogen. So the next reaction of the 3 that we're looking for is called sulfonation. Sulfonation, again, set up like a normal organic reaction, specifically for a substitution reaction. In this case, the reagent is SO3, sulfur trioxide. This is a nasty reagent to work with. I wouldn't recommend it for anyone if you can possibly avoid it, but that is the reagent that we're going to be using. And the conditions for this are a solvent system of concentrated sulfuric acid. So that doubles the nastiness. Concentrated sulfuric acid is, you have to be very careful with it, but when we're using it as a solvent in a reaction, we're using a lot of it, and trying to dissolve this fuming sulfur trioxide in it is just basically a nasty reaction all around. But we're not looking for aesthetics here, we're looking for practicality. And this, when this benzene reacts with sulfur trioxide, we get a substitution product going on. We get a sulfonated product. We're not going to give a name to this, but it is sulfonated, and the product is the product is a benzene ring which is covalently attached to SO3H. That's important. Not just SO3. It's tempting to do that because I have SO3 over here. Why don't I just put SO3 as the substituent after that substitution reaction has been carried out? No, it's SO3H. And the side product in this case is water, H2O. So this fits the bill of a standard substitution reaction. So, and again, this is all going to be set up as what's in the box. So let's take a look at the potential for what we would be looking at here. A couple of different reactions, which we can, we'll take a look at the top reaction first. Benzene plus SO3 in a milieu of concentrated sulfuric acid, we get something plus the side product H2O. All of this we have to take into account, and we would then hopefully recognize is like, oh, this is the sulfonation of benzene, so that as the product of the reaction, I'm going to put a benzene ring or an aromatic ring covalently bonded to SO3H. Very straightforward. However, if we look at the one down on the bottom now, the what's in the box can indeed be all over the place. Here we have, again, benzene treated with sulfur trioxide, and now we're asked what are the conditions over the arrow? Well, we'll pretend that the answer isn't right here on the one above, and we would say, okay, those conditions for the sulfonation of benzene are indeed concentrated H2SO4. We're given the product in this case, and we're asked for the side product. Again, I'm going to ask you to suspend disbelief because we have that the answer right up here, but we're going to pretend that these are two different questions on two different pages or what have you. So the side product would, in this case, be H2O. And the last one. The last of our three reactions of benzene, this is the nitration of benzene. And in this case, the reagent is nitric acid, HNO3. That is the source of the nitro group, which we're ultimately going to be using. Again, we have a nasty solvent system for this, concentrated H2SO4, mixing with our concentrated nitric acid. Again, just a nasty reaction. Again, we don't really care about that. We're just looking to nitrate this. And when this happens, we end up with the product of a nitro group. So we have this nitrobenzene as a product. Our side product, again, just like on the sulfonation of benzene, is water. But again, this fits together very specifically. So if we encounter a what's in the box sort of reaction or problem, we're able to sleuth it out and figure it out in a straightforward fashion. So a couple of examples. The one on the top, we say like, all right, here's a benzene ring and nitric acid in a concentrated sulfuric acid solvent base. Should tell us that these are the conditions and reagents for the nitration of benzene, so that we are going to take that benzene ring and hang a nitro group off of it as an answer. In this particular one, we also have to remember the side product. That's pretty straightforward. That was H2O, so we're filling in the box with all of the requisite structures. The one on the bottom is sort of interesting because we have to be careful to look at what, when we have a starting material as a what's in the box, what was that starting material? Look at this product right here. We have two things attached to it. And we have to be able to say, well, what was the starting material? We have to subtract out whatever was put on that aromatic ring system by these conditions, nitric acid and sulfuric acid as a solvent system. And we would find that an aromatic system would plant on that aromatic ring, would have to plant a nitro group, would have to. So what's in the box as a starting material would have to be what the entirety of what is left over from that. It would have to be. I don't know where that SO3H came from, that sulfonyl group, but it didn't come from these these types of reagents, these types of conditions. So what we would put into that box over on the left-hand side would be exactly what we picked out in the product profile. Would have to be that that sulfonated benzene already.